Okay, in this first video for section 2.7, we're going to take a look at continuity. The second video will probably take a look at the differentiability. So continuity and discontinuity. Basically, the idea of continuity is that you could trace with your pencil the curve of a graph without ever lifting your pencil off the graph. So if this is my f of x, right, and these arrows just say it goes on forever, you could put your pencil down in one spot and trace every inch of the curve without ever lifting up your pencil. Okay, but we're going to take a look at that a little more mathematically so we know what we're talking about. So here's the definition of continuity. A function is continuous at a number a, like x equals a, if f of a is defined. So this implies that the point a comma f of a exists on your graph. All right, a has to be in the domain. The second part of the definition is that the limit of f of x as x approaches a has to exist. Okay, so a point exists, the limit exists as x approaches a, and both of those things are equal. So the limit of the function as x approaches a is equal to the y value of the function at x equals a. Okay, so item number 3, where you say they're both equal, that really is the whole definition of derivative. You have part 1, the point exists, part 2, the limit exists, and part 3, they are the same. So let's take a look at this graph off to the right. Here's the graph of f of x. The yellow dotted lines are just to kind of show you what x and y value is on the graph here in case it's difficult to read. So I'd like to take a look at 4 different locations, when x equals 1, 4, 6, and 9. And we're going to decide if the function is continuous at that point. So let's take a look at the limit of f of x as x approaches 1. The limit from the left and the limit from the right are both 5, so the limit exists. Let's look at the y value of the function. Okay, f of 1 is equal to 5. Okay, these two things are equal, and so we will say f is continuous at x equals 1. All right, I'm going to abbreviate just because we're kind of short on room. All right, taking a look at x equals 4. The limit of f of x as x approaches 4, well, let's see, the limit on the left, I guess I didn't mark that, is someplace between 3 and 5. Let's just call it 4. All right. So the limit on the left is 4. Left-hand limit equals 4, but the right-hand limit equals 2. So automatically, we know that the limit does not exist. Okay, if the limit does not exist, you do not have continuity. Item number 2 says your limit must exist. So therefore, do you know the 3 dots in a triangle is the word therefore in math? Therefore, f is not continuous at x equals 4. Okay, let's take a look at the third one, as x approaches 6. So the limit from the left and the limit from the right are both 3, so the limit exists. The function value at 6 is actually up here at 5. So f of 6 is equal to 5. All right, the limit and the function are not equal. Therefore, f is not continuous at x equals 4. Okay, let's take a look at x equals 9. The limit from the left is 7. The limit from the right is 7. The limit exists and is 7. The function value at 9, f of 9, does equal 7. Therefore, f is continuous at x equals 9. Okay, you need to test all three pieces of the limit definition. Okay? The limit exists, the function exists, and the two are equal. So remember that when it says to justify that a function is continuous at a certain location. All right. So there are three types of discontinuity. All right. Discontinuity obviously means you don't have continuity. So in our last graph, we actually looked at two of the three. Okay. So here is a location where there is discontinuity at x equals 4. There is also discontinuity at x equals 6. We call the discontinuity at x equals 4 a jump. All right? Now, technically, you could call the discontinuity at 6 a jump as well. So, however, if this point was not here, I would just call this a hole. So a jump or a hole. So for example, let's say out here at 7, instead of the graph being continuous, let's say there's a hole in our graph. Okay? Then that would be a second form of discontinuity. So jump in the graph, you have a step up or a step down, and a hole in your graph. Now, there's another type of discontinuity. Okay, so let's put those on our graph. We could have a jump, we could have a hole. So a jump might be you end in one spot, but jump up to another spot. The point might exist or not exist, okay? Or it might be in another location. Okay, in either case, there's a jump from here to here to here. Okay, so those are jumps. A hole in the graph just looks like this. Okay, and the last one is an asymptote. So we could have a graph that has a vertical asymptote. Or more than one vertical asymptote. Okay, so these are the types of discontinuity that you could have. All right, so a limit exists, but there is a hole in the graph. Okay, this is the one case of removable discontinuity. They call it removable because we could plug up that hole with a point. One single point. One single, I'll call it A, f of A, could plug the hole. And that's why it's called removable. So, for example, if you had the function x squared minus 4 over x minus 2, this function has a hole in it at 2. Well, let's reduce it for a second. It's the same thing as x plus 2 when x does not equal 2, right? Okay, that's the same thing because I just reduced it. But this, I can't have 2 in the domain. So this function has a hole in the graph at 2, 4. Okay, so if I redefine the function to remove the discontinuity, it would look like this. F of x equals a piecewise function. The original function, that you cannot let x equal 2, and the value of the hole, or the y value of the function, where you're going to plug the hole. So this is the function rewritten to remove the discontinuity. Okay? So I've just removed it. All right, let's take a look at number 2. Number 2 is non-removable discontinuity. Okay, so if we look at any of these jumps, I cannot plug the gap that exists between the y value down here and the y value up here. There's too many y values in between. So the limit does not exist, okay? And I also can't plug up the space between the y values, okay? So non-removable, like a jump. Okay, infinite discontinuity is when there is a vertical asymptote. So our vertical asymptote's happening in the third example here. So the limit from the left and the right is infinity or negative infinity. So here the limit from the left is positive infinity. Here the limit from the right is positive infinity. Okay? Now, technically, the limit doesn't exist. We say the graph tends toward infinity, but for the limit to exist, it must be a finite number. So for the limit to exist, if this is x equals a, all right, we would say the limit is infinity, but this is a non-finite number. So technically this limit does not exist. Okay, the limit can only exist if this is a finite number. Okay, or you could have, in this example, the limit on the left is negative infinity and the limit on the right is positive infinity, and this definitely, the limit doesn't exist. Okay, left-hand limit does not equal right-hand limit. Okay, ask me a question about this later if you are confused about it. All right, a limit is a finite value. Okay, we will say this limit is infinity, but I can't say that that's a finite value. Okay, so it's representing the behavior of the graph. All right. Okay, let's see if we can take a look at a few of these functions and decide if the functions are, where the functions are discontinuous. So where is each of the following functions discontinuous? State the type of discontinuity. So taking a look at this first graph, first of all, let's take a look at the limit. And where do you think we're going to be taking a look at the limit of this function? What causes an issue in the denominator? How about we approach 2? Okay, if I let x be 2, I'm going to get 4 minus 2 minus 2. That's a 0 over 0. Okay, and so this function must have a hole in it. All right, I could factor the numerator. And I could reduce. So this is the same, f of x is the same as x plus 1 when x does not equal 2. Okay? So this is removable discontinuity at x equals 2. Okay, and the value of the whole would be 3. Okay, graph B. Actually, let me, you know, we're going to run out of time, so I'm just going to stop and pick up in the next video.